So now the natural question will be, what is happening with momentum when the object is moving with a velocity that is actually not constant? What is happening with momentum? Well, momentum will change, because what is happening in one moment, we will have a momentum that is defined by mass and velocity at that moment. And on the other moment, we will have the momentum defined as mass and velocity at that other moment. And if the velocity is changing, then momentum from moment 1 to moment 2 is changing as well. So now, the change of momentum is known as the impulse. So it is a unique name for the change of momentum, but it is actually the same thing as saying impulse or the change of momentum. So impulse is the same thing as the change of momentum. The change of momentum, yes, the change of momentum is like every change, final minus initial. This is what we have done when we have considered the acceleration on physics 20. We said acceleration is the change of velocity over time. So, and any change is always final minus initial. Okay, now if at a final moment we have a velocity final, then we can say that this is mass times a final velocity minus mass times initial velocity. And this is simply from expressing momentum initial and final using mass times velocity. Okay, for the velocities that we are discussing here, mass of the object is not changing. So we are talking here velocities that are not that large or close to the speed of light. Therefore, as a result of this motion, the mass of the object is not changing. You may ask me, why are you stating this? Because we will see at the very end of the course that when the object is moving with a high speed, close to the speed of light, the mass of the object is converted into energy, is changing into energy. So for what we are doing here in mechanics, because momentum and impulse are part of mechanics or Newtonian physics, mass of the object for those velocities is not changing. So we can easily factor this out and say that momentum, or the change of momentum, or the impulse, is equal to mass times v final minus v initial, which, what was this? I just mentioned it, is the change of the velocity, mass times the change of velocity. So now we can say that, yes, momentum is mass times velocity, and momentum at instantaneous has the same direction as the velocity at that moment, but the impulse has the same direction as the change of velocity. Okay, make sense? So the impulse or the change of momentum will have the same direction as the change of velocity. Now let's bring this, only this part here. The change of momentum is equal to mass times the change of velocity. This change of velocity is happening at a certain time. So now and time is a scalar quantity, and it's always positive because we start from this moment and on. So if we divide both sides by the time that this change is happening, mathematically, I'm not doing anything wrong. Mathematically, what I'm doing is I'm dividing both sides of a relation by the same number, positive number. So I'm not changing the sign, even when I consider it as a vector. We are not changing the sign. And since we are dividing both sides by the same number, we are not mathematically doing anything wrong. But by doing so, what we are able to see is that now we have the change of velocity over time, which actually is what from dynamics or kinematics. Delta P over delta T is equal to mass times acceleration. Is that right? Okay, so mass times acceleration. So now we can say that the change of momentum has the same direction as the change of velocity, and it has the same direction as the acceleration as well, because actually we know it from kinematics that acceleration will have the same direction as the change of velocity. And you can even see this from the relationship, because this is mass is a scalar, change of time is a scalar. So what you're doing is a vector in one side is the same direction as the vector on the other side. However, by writing the change of momentum over time as mass times acceleration, and knowing from physics 20 that mass times acceleration is equal to force net, then we can say that force net is equal to delta P over delta T. And actually, even though that we teach you that force net is equal to mass times acceleration, when Newton presented to us the principles of physics, he said that force net is the rate of change of momentum. And this is what he said, what he actually said, is the rate of change of momentum. But now, since based on the progress that you had in math and on physics, usually saying that force net is equal to mass times acceleration is taught to you prior to force net is the rate of change of momentum. So now from here, we can see that the change of momentum or the impulse is equal to force net times time. And again, what do we have here? If we know the direction of force net or the direction of the impulse, then we know the direction of impulse or the direction of force net, because the change of impulse, the change of momentum or the impulse and force net have the same direction. Make sense? Now, if we have a graph that represents the function of force, of any force, this being force net, then we will calculate net change momentum, but any force versus time, then the area under the graph will represent the change of momentum. So if it is a triangle, then the area of a triangle will be 1/2 base times height. So will be this area here. If it is a rectangle, force versus time, then this will be equals to the change of momentum. The change of momentum in magnitude, but since it is positive, then will be positive, whatever is the positive direction that it is assigned or it is assumed to be, base times height. And if it is a trapezoid, if it is something like this, then you can solve it in two ways, either divide it into a rectangle, area 1 being a rectangle, base times height, and area 2 being a triangle, 1/2 base times height. Or you can use the area of the trapezoid is 1/2 small base plus large base times height. And this will be the height. To summarize, how are we seeing impulse, which is the change of momentum, from the perspective of Newton? We can say that the first way that we calculate the change of momentum or impulse is when we are literally subtracting two vectors together, momentum final minus momentum initial. And then the second way is to calculate the impulse or the change of momentum is if we know what is the velocity final and velocity initial and mass. The third one is when we have, so this will be mass times this will be force net times time in which the change of momentum is happening. And the fourth one will be when we have graph. Now, from this relationship here, we can draw the conclusion that momentum or the change of momentum will have the units of newtons times seconds. Okay, because force net is newtons and time is in seconds in international system unit. So the impulse or the change of momentum will be newtons times seconds. But when we see it from the first two perspectives, the change of momentum still will be kilograms meters per seconds, kilograms meters per seconds. However, newtons times seconds and kilograms meters per seconds are the same units. So newtons times seconds is identical with kilograms meters per second. Because when we are saying newtons, we are saying mass times acceleration. So when we are saying newtons, we are saying kilograms meters per second squared, and then times second and second is canceled out. Then you have kilograms meters per second. However, when we are talking about momentum, then the units that you are asked to record your answer is, in 100% of the cases, kilograms meters per second. And when you are asked to calculate impulse, which is identical to the change of momentum, the units are usually in newtons times seconds. And the reason for that is just to make a distinguish between the fact that we are dealing with momentum or instantaneous momentum and the change of momentum. Good.